So we'll just wait 3 more minutes before we start to allow more people to come. Thanks. Good evening, everyone. Welcome to tonight's AGS Technical Evening Talk. I will be your MC today, Roger V. And today we have a very exciting presentation for you. It's Sissterra technology, a 3D passive imaging solution for subsoil exploration in urban context by Dr. Maria Sade and Clement Mogenier. So before we start, you can enter your comments or questions in the Q&A box below, and they will be answered afterwards. And also your CPD certs will be issued in a few days after this presentation. So just a quick go through of the synopsis, it won't take too long. Sissterra is a 3D passive tomography solution for imaging the subsoil at high resolution. And about Dr. Maria Sade is currently an expert in seismic method and mainly the Sissterra solution for Sixth Sense Group in Nanterre, France. And Mr. Clement Mogenier is currently a senior PM for Sixth Sense Group in Lyon, France. So welcome, Clement and Dr. Maria, for joining us, and thank you for keeping our evening talk AGS Hong Kong lively. Thanks. And today we have a lot of passionate participants that are interested in this topic. Right now we have around 90 participants. So again, thank you for your support. And without further ado, I ask Maria and Clement to invite you to speak and present. Thank you.
Thank you, Roger, for this kind introduction. Good evening, everyone. Josan. Tonight, we will present Sissterra, which is, as you said, a 3D passive imaging solution for subsoil exploration adapted to urban context. After the introduction, we will present the main theoretical principles of this technique and explain how it is implemented in the field. Then we will present recent case studies of projects where the technique has been deployed for infrastructure projects. This presentation will last 30 minutes approximately, and we'll finish with a Q&A session. Let me introduce myself first. Clément Mogenier, project manager for 6 Sense with 17 years experience. I've spent several years of my career in Hong Kong working for major projects like the West Island Line, Contract 703, the South Island Line, Contract 904, the Sha Tin to Central Link in Wan Chai, and other projects in Asia and Oceania, like the Nam Toon hydropower dam or the Metro Tunnel project in Melbourne. And Maria, can you introduce yourself?
So, hello, my name is Maria. I work at 6 Sense since 2019 as a seismic expert and seismic methods, but mainly on the passive seismic tomography that we will present today. Before that, I held a PhD in seismology on passive seismic methods and several postdocs in different fields in seismology, planetology, planetal seismology, and applications also in Japan. Yeah, that's it. So, Clément.
We'll move to the next slide. So, globally speaking, the land use density is increasing, as you can see on the pictures here with the city center of Hong Kong. And the multiplication and the complexification of urban construction, especially for underground infrastructures in such crowded environments with existing metro lines, existing foundations, require to adapt the projects and to overcome these limitations. And you can see the picture from the Czech Lapkov airport here. The limitations are not always coming from the existing infrastructures, but also from safety standards, like working with low headroom restrictions, as it was the case on this airport project. As we are all aware of, we need to reduce our carbon footprints, and including for the site investigation techniques. And Sissterra can help reducing the carbon emissions of site investigation works. Next slide. So geological and geotechnical models for infrastructure projects are mostly based on site investigations and geotechnical tests. And those tools, of course, are reliable and efficient. Bill, I think can you turn your mic off, please? Sorry. So site investigation, like core drillings, SPT, and other in situ investigations are still reliable and necessary to geotechnical designers for their own calculation. But in such a restrictive environment, it can provide some sparse information and only provide only a few % of the soil information, as sampling is not already easy in such conditions. So this is why we had the conviction that a new technique has to be developed to provide a comprehensive answer to the soil investigation, and that is easier to deploy as well in constrained environments while keeping a low environmental impact. So Sissterra was created with that in mind to consolidate and improve geotechnical models. Next slide. Of course, to complete those site investigation works, conventional geophysics is currently applied or has been applied widely for infrastructure projects. The main thing of conventional geophysics is that it requires to install sensors, lay cables on the ground, sometimes to use this kind of seismic trucks. That is not easy to deploy in city centers. It's not really accepted by third parties. And also it requires to use active sources of noise, active sources of electricity, which are sensitive to environmental disturbances, so the noise. And generally, the energy we generate with those sources is much lower than the energy contained in the ambient noise. So that may limit the possibilities of conventional geophysics when the environment is too crowded, too noisy, with too much activity. This is why Sissterra has a scalable, flexible solution and a cable-free solution can make use of these environmental disturbances, the ambient noise for subsoil exploration. So using all this energy contained in the ambient noise to investigate the soil. This is the general idea of Sissterra. Can move to the next slide. Who are the potential users or the current users of Sissterra? So project owners. We have a project now in Saudi Arabia for a project owner who wants to know more about the geological model of his project. Of course, construction companies, when they encounter soil conditions that are not as simple as they thought and anticipate geotechnical difficulties. Engineering companies to propose innovative techniques to their client and optimize site investigation budgets. Transportation operators, of course, because they need to undertake the maintenance of their assets and anticipate any geotechnical risks in the future that could affect their operation and their turnover for sure. And what are they expecting from this new technique? It's offering a 3D overview of the underground and give comprehensive information. Be able to work in constrained areas with very low disturbances for the third parties. Also to integrate those low headroom restrictions, for instance, all the restrictions and the safety standards that may prevent for implementing conventional investigations. And an ease of deployment with a limited number of procedures like TTMS, traffic management, and so on. Next slide. So after this presentation, this general presentation, my colleague Maria will explain a bit more about the theoretical principles and the implementation of the technique.
First of all, excuse my voice. It's the virus season. So if you can't hear me very well, please don't hesitate to say it. So let's start about the main principles of the passive seismic 3D tomography. So it's mainly based on the use of passive ambient seismic noise. So passive means that we do not use an active source, such as any kind of source, explosion or weight drop, etc., in order to emit a seismic signal and analyze it. We use ambient noise signal, that is noise emitted in the surface by different types of sources. Here at an urban scale, we use sources such as any human activity, transportation, construction sites, even atmospheric phenomena that can happen on the surface between about 1 and 100 hertz. These sources, they also emit seismic waves that can propagate in the shallow crust and the shallow layers. And then when we collect this noise and extract the surface waves that are hidden in the noise, we can analyze the crust. So that's a very big advantage of this method, because we do not need to use a source that can emit any waves. We just use the noise that is present everywhere continuously. But as you might imagine, we have a noise signal, and it's not easy to extract waves from the noise. So there's a mathematical procedure that is applied on this noise that we call cross-correlation. I will detail this later. So cross-correlation, or what we can call as well seismic interferometry, is a mathematical procedure that can allow us to extract the seismic waves that are hidden in the noise And that way we can measure the shear wave velocity, which is the speed of these seismic waves, and then have a 3D image of the subsoil in terms of shear wave velocity. So our observable, or the parameter that we measure, is the shear wave velocity. That is a physical parameter that can give us a lot of information about the quality of the soil, and that is related to the shear modulus, and from which we can extract or compute that geotechnical modulus. Just before I start explaining more about this technique, this theory exists from the 70s. It was developed, the seismic interferometry, or the cross correlation, was developed in the 70s, but the first applications started in the early 2000s because the technique needed a lot of computing resources that did not exist before. So here, what I show you here is the first study for the first application that was published in 2005 for this application of 3D seismic tomography. So this application is, of course, on a larger scale. It's on the scale of California. And the aim was to image the crust in California using US arrays. So here they used about 62 stations on, of course, a larger scale, 1,000 kilometers. For this study, they measured the ambient noise for about 1 month. So they collected data for about 1 month, and they applied the 3D tomography as we see here. This is an image of the subsoil. These, the colors represent the velocity, the shear velocity variations along the area of study for a period of 15 seconds. So here, of course, it's a larger scale. So the noise that we use is not the noise that is emitted at a smaller scale, at an urban scale. It's mainly what we call the microseismic noise. So it's a noise emitted by larger sources that are mainly the interaction of ocean waves with the soil. And that what they did observe here is velocity anomalies, as we see here, the different colors, that they related to the main geological structures, in particular low velocity anomalies, that they might correspond to the main sedimentary basins, and high speed anomalies that might correspond to the major mountain ranges. So again, this is a research study, one of the first research studies that published this method, and since then the methods was more developed and more applied. Here I show you another study, again in the academic from the academic in 2017. So just so you know, the method is still in a research and development phase, and we're still developing, we're still discovering further applications and making it more applicable. And this is another study, more recent, which was applied for in order to observe variations along strike in the Himalayan orogenic wedge structure in Bhutan. Again, using ambient seismic noise tomography. So this study, again, it was on a larger scale, about 300 kilometers, and it allowed to image the subsoil from the surface down to 18 kilometers, using also waves at a lower frequency between 0.05 and 0.5 hertz. And what they did observe is several high shear velocity anomalies that might correspond to tectonic windows of clipping at the surface, and probably formation of localized duplexes of quartzite lithology. Okay, so after the development and the publishing of this method and at the universities by researchers, at Sixth Sense, we had the first collaboration with the university and the researchers that developed this method in order to apply it on a smaller scale at Sixth Sense and apply it as and use it as a solution in applied seismology. So I'll just brief the different steps of the solution from the acquisition to the data mining and the data analysis. If you have questions about the details, please don't hesitate. So let's start with the acquisition. The acquisition is about deploying a dense network of seismic nodes on the surface of the study area. So we deploy nodes, autonomous nodes, so wireless and very easy to deploy on the surface. The design of the network is prepared before, depending on what we are looking for in terms of depth of investigation and a resolution. So usually the distance between the nodes should be equivalent to the lateral resolution that we are looking for in our final result. And the dimension of the network should be depending on, of course, it should cover the area of study, but it should also be designed as a function of the depth that we need to image. The deeper we need to go, the larger the network needs to be. So we deploy these nodes. The network does not need to be very regular. At the contrary, and that is a big advantage, especially in urban areas where it's very difficult sometimes to deploy a very regular network and a very straight line and a very strict interstation distance. So we deploy these wireless nodes and we keep them for a few days. The time is also defined depending on how much ambient noise we could have in the area. So why a few days? Because we need to collect as much noise as possible in order to have a good signal and a good result. And yeah, we usually work on hundreds of meters networks, and we deploy the dimensions. This solution is really can be adapted to any scale, and we deploy as much nodes as we need depending on the resolution that we need to have. It could be 100 nodes, it could be tens of nodes. It depends on what we are looking for and how much resolution we need. So when we collect the data, we have a raw signal. So as you might imagine, we cannot extract anything from a raw signal if we take it as it is. So we apply this mathematical procedure that we call cross correlation. I'm not going to go into details, but if you have questions, don't hesitate. So this technique is about computing a cross correlation between pairs of receivers. So we do not take just one single node, one single seismic record. We take two and we compute a cross correlation between them. This procedure allows to extract the seismic waves. We usually work with surface waves that propagate between these two nodes. That way, we could extract the propagation time of the wave between two different nodes, and then have a velocity measurement of the wave between these nodes. So if we have, let's say, 80 nodes, as what we have here in this network, we could have more than 3,000 pairs of receivers. So that way we could have more than 3,000 measurements, because we have one measurement by pair of receiver. And that is a big advantage, another big advantage of this method, because this way we can increase the number of measurements. Because if we do have 80 nodes, we don't have only 80 measurements, but more than 3,000. And then the 3D velocity model that we get at the end is a combination of more than 3,000 measurements. And that is why we consider this method as much more reliable than any other conventional solution. So at 6 Sense, we've been applying this method since 2016. Today, we have more than 20 references in different contexts, different application, construction sites, TBM, for seismic assessment, for risk assessment, for major decisions related to risk or construction. So we're going to present later some main references that we have. And we have a solution that is 100% operational, from the design of the solution to the acquisition, to the data processing, to finally the result analysis. And we do have a high processing capacity at 6 Sense because we need that in order to process large quantities of data and process this high number of measurements with the cross-correlation technique. Now, compared to other conventional solutions, Sissterra is considered as a very suitable and adaptable solution, since it can be applied in different contexts, mainly urban contexts, since we can design the network depending on the area. As I said before, we don't need to have a very straight and very strict network. It could be adapted to the area of study. And we do not need to use a seismic source, which is also a huge advantage, mainly in urban areas where most of the time it is not possible to use a seismic source, such as an explosion or a weight drop or a smaller source that cannot emit signal at a long distance. So with Sissterra, we just need to deploy the nodes and just leave them to record the noise that is already present in the area. And the solution, the Sissterra, allows to have a 3D complete velocity model, which is a complete detailed 3D measurement, and that could allow to have measurements that complete the geotechnical solutions that usually present 1D, a very punctual measurement. So usually when we have like drilling how to say this, informations, geotechnical, very punctual informations, we don't have any information about the soil between the different measurements. So Sissterra could allow to have this complete 3D imaging. And again, it's a very relatively highly reliable and robust method, since it's the result is obtained by the combination of a very large number of measurements. So now we're going to present different case studies, mainly 4 in different contexts. So Clément is going to present the first one.
Yes, thank you, Maya. So let's start with the first one, which is, so Sissterra technique is not only deployed for large infrastructures projects, it's also scalable to smaller projects like this expertise here. This residential building is affected by major cracks up to 10 centimeter displacement between the 2 blocks here, as you can see on the pictures highlighted in red. So the inhabitants are still living in the building and using all the facilities, the parking lots, and so on. So in a first approach, the geotechnical engineer and the owner of the building were looking for lightweight solutions and a non-invasive solution to bring information on the origin of these cracks, very likely coming from differential settlements. So the sensors have been installed all around the building. You can see the green dots on the layout here, and without any annoyance for inhabitants. So it's very discrete. Ambient noise has been recorded for a few days before retrieving the sensors and then analyzing seismic signals. Once again, no active source were used. We are just listening to the ambient noise for a few days. Next slide. The results we obtained after listening the noise and processing the seismic signals is a quite simple 3D model of shear waves velocity that revealed 2 layers of different stiffness, of different shear strength, and competent materials. So the second layer was found at different depths across the building, ranging from 5-meter depths in the northwestern part of the model to 10-15 meters depths in the southeastern part of the model. This information is relatively simple, but it was reinforcing the assumption that cracks were coming from differential settlements, as the thickness of the compressible superficial layers that shows low shear strength is varying below the building. So after this survey, after this 3D evaluation of the shear strength of the materials, it was proposed to drill few boreholes to calibrate the seismic velocities. You can move to the next slide. So 2 drillings, 2 boreholes were drilled on both sides of the buildings at locations where the Sissterra survey revealed different depths of the competent materials to have in situ evaluation of the soil properties. So the drilling logs revealed that the different geological layers were found at similar depths. I mean, the marl layer that we observe at minus 13 meters is found in both boreholes at the same depths, except that when we look in details the drilling parameters, it appears that the drilling speed is indicated in yellow here, is varying a lot within the geological layers. That means even though the geological layers are quite regular, there is different weathering state of the materials in the marl layers, and the very top of the marl layers, the 6 to 7 meters at the top of the marl layers are softer, or at least they present some low geotechnical properties, geotechnical characteristics. It suggests that weathering state can vary laterally below the building, and maybe explaining the differential settlements. As you can see, there is a 6 to 7 meters of weathered materials in SD1, so the borehole on the right. It confirms the result of the Sissterra survey that also shows a difference of 6 to 7 meters in the depths of the stiff materials. So it's very important, this fact that has been confirmed by the drilling logs. You can move to the next slide. These are the results of the 3D investigation. So it's basically the illustration of what I said. So from the west to the east, the stiff layer is dipping. We found it quite shallow in the west to find it deeper in the east of the 3D model. That has been confirmed by drilling logs. So we don't have any historical information about this building, about the founding system of the building. So we can imagine that maybe in the 70s, the geotechnical survey was not complete enough. and it didn't reveal the variation of the geotechnical properties all along the buildings. So that may explain now that we have some differential settlements if the funding system is not well adapted, and if the pile system is not going down to the stiff materials, then that may explain the differential settlements we observe now, and then the cracks we have on the buildings. So that was the first example of how Sissterra can be used for very simple projects with a limited number of nodes. That means it's not necessarily a very complex installation. It can remain relatively simple. By installing just 30, 40 sensors, it takes 1 day. And then after a few days of listening, we can obtain this kind of 3D model below an existing building. So we can now move to the next case study. The context is a bit different. We are in Oman in the Middle East. This is an industrial site, a power plant that is affected by settlements and sinkholes at surface. So it's something that can be assessed by conventional drillings, of course. But in this case, the site is really complex with a lot of buried utilities and buried structures. So the client wanted to avoid any destructive means to avoid any trial pits for approach to the existing utilities and so on. That requires a lot of time, a lot of budget to drill just few boreholes. So this is why 100 geophones were deployed over the survey area at a resolution of approximately 10 meters between geophones. We have recorded the signals for a week approximately, to reach a depth of investigation of 30 meters. And the purpose was to image the weak zones and the bedrock to try to understand the origin of the settlements at surface and the origin of the sinkholes. And we see some pictures of the site with all those utilities that are present in the survey area. So it's quite complicated to drill within these conditions. We can move to the next slide. So this is the final model we obtained using these 100 geophones. The geological model, geotechnical model is quite simple, but we observe two different layers. The first layer of low geotechnical properties that corresponds to the backfill materials and superficial deposits. And in blue here with high velocity materials, we have the bedrock, or what is interpreted as the bedrock, at least stiff materials, competent materials. So globally speaking, we have compared these results to the observed settlement at surface and the sinkholes locations at surface to understand the correspondence between the two. And it appears that the settlements and the sinkholes are generally related with the most important thickness of soft materials in the first layer, and also where the seismic velocity in this first layer is the lowest. That means where the shear strength is also the weakest. So there was a good correlation between the two information, observation from the surface plus the VS velocity model. And just a conclusion about this case study. So the main fact for the client was to avoid any drillings and avoid any risk for the existing installations, avoid any risk for the operator, the drilling contractors as well, as the utility risk is real on this project. So we can now move to the case study number 3, presented by Maria.
Okay, so this study is very recent. It was in Luxembourg in a tunnel area. So in the study, we had to improve the method even more after several applications that we had at 6 Sense. because before what was possible is to deploy a seismic network on the surface and to analyze the subsoil from the surface down to a certain specified depth. And usually the seismic waves that we analyze, they do not propagate in the void. So if there is a presence of a void, of course, it depends on its dimensions also, but if there is a void in the soil, in the crust, whether it was a large cavity of a void or a presence of tunnels, usually this can perturbate the propagation of seismic waves, and it can hide what is beneath them. So it wouldn't be possible to observe what is happening beneath these tunnels, for example. But for this application, we had an area with two tunnels that are parallel, and we need to image the subsoil around these tunnels. And what we did was deployment of a network on the surface
Small sound issues. Maria is coming back, so. Okay, then I will continue. Maria has some connection troubles. So the sensors have been installed in the tunnel as well as in surface to improve the geotechnical model beneath the tunnel, and also to complete the information that has been obtained from the surface. Let me contact Maria, make sure she's still with us. I hope Maya is coming back.
Apologies, some technical issues now.
Clement, you want me to share the PowerPoint for you?
Yes, you can share the PowerPoint, and I will finish the presentation.
Yeah, let me do it. Hold on.
So I take this opportunity to invite young professionals under the age of 35. You may submit a 500-word report on this event, and the eligible winner will have an AGS book prize report based on the assessments. And prize comprises of Geology of Site Investigation Boreholes in Hong Kong by Chris Fletcher, and a book coupon of $500. So you may send your 500-word report to Hayden Chen on this evening talk. So again, thank you for joining. So is it
okay?
So we go back.
Cameron?
Yeah.
Yeah, we can continue.
Yes, we continue now.
Yeah, go ahead. I will flip the PowerPoint for you.
Yeah, okay. So you can see the installation here. The red dots are the installation at surface, and the yellow dots are the installation in the tunnel to obtain more reliable information in depth. You can move to the next slide.
So Hayden, you can change to full screen. Right now it's a presentation.
Okay.
Screen.
So how can I?
On the top display settings, on the very top left.
Oh, okay. Huh?
See?
Sorry.
Display settings.
Okay. Should I
Duplicate.
this one? Okay.
Yes.
Yeah.
Yes, perfect. So you can see a 2D section across the tunnel here. And you can see the existing foundation of the tunnel. Maria is back, perfect. You can go on, Maria.
I'm sorry, I don't know what happened. I wasn't aware. I was talking alone. Okay, so I don't know where we were. So what I was trying to say is that it's a very new application which we applied also nodes and was to analyze the subsoil around the tunnels where they did observe some settling and swelling areas.
Can you try to switch off your video?
And yes, yeah. Okay, I did that. Okay.
Yeah, thank you.
Okay, so next slide. So I don't know if you have the video here. Can I share my PowerPoint? Can you hear me?
Yes, sure.
Okay.
Yeah, sure. I turn off.
Okay, I'm gonna share my PowerPoint now because I have a video to show. And okay, so in this video, we see the final result visualized with our software, in which we see the 3D velocity model down to about 60 meters depth. So velocities that vary between 300 and 1,200 meters by second. And we see the results obtained from the surface network and also the ones obtained with the network deployed in the tunnels. So we get to have an image, a detailed image between beneath the tunnels, which was not really possible with the surface network. And what we were mainly looking for was the anomalies that we can have in these measurements, in these velocity horizons that we see here. So as we see in here in this video, in this model, we filtered the velocity and we focused on the low velocity in order to see if we can observe low velocity anomalies in the horizon, in the bottom horizon. And we see here some low velocity anomalies here in these areas. Two of the main anomalies were also observed on the borehole geotechnical analysis, but we also observed another area of low velocity on the other side of the entrance of the tunnel. So these results were very important for the client that was actually looking for a detailed image of the subsoil, same as Clément said before. With the boreholes, we have a very punctual result, but we don't have a complete result. So we could have a hint or a proof that there's an altered material somewhere that could cause risk on the surface, sinking risk, or any collapse risk. But we do not have any information about the dimension of these anomalies, and we cannot delimit them. So when we have a 3D image as this one, we can at least delimit the presence of these risky material and altered material using this 3D high resolution details image. And for this client, it was very important to have to delimit and to know the risk related to these areas in order for the client to have a better decision making related to the destruction and the rebuilding of these tunnels. Another application is also very similar to the Oman application that Clément showed earlier. It's also in an industrial complex in Morocco. This industrial area is very large, a few kilometers large, and they identified in this area the presence of they observed some evidence of soil collapses on the surface that could probably be related to the presence of karstic cavities under this industrial facilities. But as also Clément said, it is not possible to, in this kind of context, in this kind of area, to have boreholes everywhere in order to detect all the presence of cavities. So we did we applied the 3D passive tomography in specific areas. In total, there were 11 areas, each of 200, 300 meters dimension. These were areas where that were considered as risky and very important for the client we had. And in each area, we deployed a seismic network, and we had a 3D passive imaging. So again, these are photos of the area of study. So as you might imagine, it is not really possible to apply any kind of conventional active method. So we did deploy a seismic network of autonomous nodes. As we see here, they're very small, very easy to deploy, and the network does not have to be regular. And the final result was a 3D imaging of the shear velocity measurement. So here I show two main results of two main areas. One is located here and another one here, I guess. And these are shear velocity measurements down to 30, 40 meters depth. So this was the depth that was mainly interesting for the client. And what we were looking for was, again, these anomalies of the velocity that we could observe in these homogeneous seismic horizons of shear velocity. So we did have general information about the geological structure as the identification of the different seismic horizons, but we were also focusing on these anomalies that we can observe here that might be related to the presence of cavities. But again, they might be, but we cannot be sure that these are cavities. What we can say is that we can observe low velocity anomalies. They might be related to presence of cavities, or maybe the presence of altered material. So we suggested to have some boreholes at these very specific areas where we did observe these low velocity anomalies, in order to make sure with some geotechnical analysis of the nature of these anomalies and make sure if they're related to some cavities or not. But this 3D detailed image allowed to detect the presence of potential cavities and delimit them in the 3D space. So these were our applications, our main applications. So now if you have any questions about the theory or the applications or the solution in general, don't hesitate. We'll try to answer all of your questions.
There is a question from Elias in the chat. Is there a max distance between the nodes? The distance between the nodes depends on the resolution we need to achieve. Maria said the spacing between the nodes is approximately the resolution we obtain, the lateral resolution we obtain. So if we need a 5 meter resolution, then the spacing between the nodes must be 5 meters.
There is no really maximum. It can be applied at different scales, at the urban scale, as I was showing, but also at a continental scale, as I showed in the publications, academic publications. The only difference is that the resolution, as said Clément, and the sources the type of sources that we will use will be different. So the frequency will be different, and the lateral and vertical resolution will be different. We cannot have, for example, a very detailed information about the first meters, the first shallow meters, if we have a spacing of 100 of meters, of few kilometers.
And there is another question from Elias. Was the system tested in marine environment? Yes, we are currently testing the system for a dam project in France, and there is a river crossing survey. So we are currently installing the sensors at the riverbed, and we'll analyze the signal very soon. So it's still in development, but yes, the next step is to use it in a marine environment. And then, Maria, maybe there is another question from Gary Lee. Can the sensor be installed on the hillside terrain I guess, for landslide survey? And if not, what is the max slope we can have for installing the system?
So it's a question about the topography?
Topography and the use of Sissterra for landslide survey and hillside surveys. Okay,
so the best is to apply the method on a plain area. The topography is acceptable if the slope is continuous, or if the topography variation are small relatively to the design of the network and the distance between the stations. And when it comes to landslide, maybe the only risk is that the geophones won't be fixed, because it's very important that their location would be fixed. But then when it comes to topography, if the topography is continuous, it wouldn't be a big problem. Any other questions?
Yes, there was one from Ian Joseph Solomon. What is the total cost for a study? Maybe that's a bit sensitive right now.
Yeah, it's a bit sensitive, but in terms, if we compare with other techniques, the fact is that Sissterra is a comprehensive technique that covers generally large scale areas. So the cost could be a little bit high compared with other techniques, because the survey area is also quite big. But as we presented for the building case studies, it can be adapted to smaller surveys. So it really depends on the number of geophones we want to install. For sure, 30 geophones is not the same cost as a survey with 300 geophones. So it's really, I would say this is the same cost as conventional geophysics, except that the size of the projects generally can be a bit larger. So, but it's not very different from conventional geophysics.
There's another one, anonymous attendee. Thanks for the presentation. Do you think this technology has the potential to detect or estimate the thickness of core-stone zones commonly encountered in granite? Will it be challenging, as the size of the core stone is generally in the order of a few meters?
For sure, the core stones are quite small objects compared to the resolution we can have with this technique. So we are more prompt to see, I would say, the upper fringe or the weathered layers of the granite. To evaluate the thickness of the CDG layers itself, but we are not going to identify each core stones. If core stones are present within sand materials in depth, we will record an average velocity of the medium, but we are not going to identify each core stones just by taking into account these resolution issues. There are other techniques for detecting core stones, but Sissterra is not initially designed to detect deep core stones.
Another question from a gentleman, KM. Let's call him KM. How do you decide the number of nodes? is 5 meter the standard length? I guess that's the plan dimension or the spacing.
The number of nodes is decided depending on the design of the network, on the dimensions of the network, and the resolution that is needed. So no, 5 meters is not a standard length. It could be adapted, as we said earlier, but yeah, it could be 10 of nodes. It also could be thousands of nodes. It depends on the dimension and the resolution.
I'll skip to one by Dennis Lombardi. How do you deal with spatially and time-varying ambient noise, especially in industrial sites? Any impact on the final subsoil image?
Yes, of course. That's a very good question. It's one of the main conditions to carry on with the data processing and get the final image. We do test the variation of the source, because there are two conditions. The source should be present everywhere, or could have a very specific incidence, and that's a condition that is verified, and we change the parameters of the processing according to this. And we actually, just one more information, we actually collect data for more few days and the more time possible, in order to have data that comes from all directions and have a signal that comes from all directions. I hope I did answer the question.
There's two more questions. Can it be, by Gary Lee, can it be installed in hard surfaces or concrete pavements, etc.?
Usually when we have a hard surface or a concrete pavement, we do a small borehole, and we deploy the node as deep as possible. The important thing is that the node would be correlated with the soil, not correlated, but in contact with the soil.
Just to reply this question, in a previous case study shown by Maria, we have installed the sensors in tunnels. So yeah, I would say yes, we can do it. We need to avoid the installation directly on structures and foundations, but a concrete pavement or asphalt pavement is not really an issue.
Question from another anonymous attendee. Is it possible to keep installing new nodes at the excavation phase in a tunnel to foresee problematic zones and constantly review it during the construction process? Any durability concerns?
No, we didn't do that. There are some experiments in the academic research with the installation of sensors in boreholes at the front of tunnels, or I would say to survey more complex geometries with 3D networks. But we are not at the stage of installing sensors at the front of the tunnel and have the real-time image of the soil. That's not yet possible. So what we can do is to install the network above the TBM project, for instance, and leave the sensors during the excavation and record periodic images of the soil and assess the difference between the two images, two successive images. This is what we can do, but it's not really real time.
One from Ian Solomon again. Have you had security issues, theft or vandalism of unattended nodes?
That's a good question. Depending on the context, on the cities, on the urban context, we can work with security guards basically for keeping an eye on the sensors. And we generally try to hide the sensors in the bush or to keep it as discreet as possible. We had few sensors that have been stolen in Paris project, but only few. And generally, people don't really care about the sensors if they are not in the middle of the street. So we try to hide the sensors as much as we can, for sure. But we had a couple of them that have been stolen. Yes, it happens sometimes.
I have a quick question. So when you do the survey, seismic survey, is there any indication of where the groundwater level is? Can you see that?
Maybe Maya can answer. But water is not, we are recording shear waves velocity, and the water has no shear strength. So that means there is no big difference in the shear waves velocity if we are above or below the water table. Of course, it changes a little bit the pressure between the different I would say grain of soils. So it has a small effect on the VS velocity, but basically, theoretically speaking, there is no shear strength in water, so it doesn't affect the VS velocity directly. It's not a technique that can be used for assessing the water table.
So we have time for one last question by Elias again. Can soil resistivity be extrapolated from the array?
No. We are using seismic nodes. We just record the vibrations, and on the sensors there are no electrodes for recording the ambient electrical current. So we are not measuring the two at the same time, the two parameters at the same time. If we want to compare, to add an electrical image of the soil, we need to deploy a 3D electrical survey at the same location as the seismic survey, but it's not using the same sensors. We have to deploy another type of sensors, another type of electrodes.
Okay, thank you for that interesting talk. I can see a lot of merits in this using ambient noise to detect the ground model. It's a good ground investigation means and it's easily accessible to install these instruments. Thank you again, Dr. Sadie and Mr. Mojeni. Thank you for your support for AGS Hong Kong.
Thank you, Roger. Thank you, AGS then. And
very interesting.
Yeah, there is a lot of noise in Hong Kong. I'm sure we can find some applications.
Yeah. Yeah. So if you still have questions, you may email Hayden Chan and we will forward the question to Dr. Sadie and Mr. Mojeni. And also you will get your CPD certificates in a few days. And of course, a reminder for the young engineers, you may submit a 500-word report, and the winner will be eligible for book prize and the $500 coupon. So thank you again, the speakers, for supporting AGS Hong Kong, keeping our industry passionate. And I hope to see your technology being used in Hong Kong, because I can see a lot of conditions which can be used, especially in karstic sites and the marble sites in Hong Kong. Hopefully, we'll see these nodes being used. So this brings us to the end of our evening talk. Thank you again, and thank you.
Thank you.
Have a good evening. Have a good Friday night evening.
Good evening, everyone.
Thank you. Bye-bye, everyone.
Right. Cameron, thank you very much. Huh? Cameron,
Thank
how
you,
are
Raymond.
you? Thank you and Maria to have a delivery for us. Huh? Hoping that we have chance to have this kind of talk again.
Yeah,
your
sure.
your geophysics topic are very interesting, but very difficult for me.
Thank you, Raymond.
Okay, when it's come to Hong Kong, we can have a meeting. We can have a talk again, a chat.
Sure.
Okay,
See you
thank you.
around in Hong Kong. Yep.
Bye bye.
Bye-bye.